calculation. Okay, so like I said, guys, yesterday, grab your calculator, the sheet that we did the calculation. I modified our sheet. Let me show you what I've. Well, let's just see the sheet that you guys have. The sheet that we did yesterday. Quick. No, not residential, commercial. And let me just, where am I here, Chad? Okay, load calculation. And let's go to here. Okay. Okay, do me a favor, Zach, my friend, I'm gonna start here. So you might have to kind of, I didn't say that. You didn't even hear me. Okay. All right. Can you guys grab this sheet? Make sure that this sheet is handy. Um, okay. Can I start, guys? If you want to go continue outside, you can talk outside. Really? You? Okay. No, I mean it's just so here's the sheet that we're gonna be doing today. So please follow it step by step. Make sure you have it. I'm not gonna write the code articles because they're right in here. So so everybody got that one from yesterday. So let's go ahead and start with okay. Here's the problem that I have. I have a building. Let's just write the one that the requirement first. Or which let's just start with the building that we have. I have a building and multiple panels that's coming out of this building, very similar to the our project, very similar to our project. And I need to do the following. I'm bringing power to the panel, taking power out of the panel into each one of these panels, right? Going all the way. So I'm taking my power in. And I'm also pulling an equivalent grounding conductor, a neutral here. This is my neutral. And I'm bringing a neutral to this panel and a neutral to this panel. And I'm bringing a neutral to this panel. I also have a grounding bar. This is ground. And I need to bond. This is my bonding jumper in the service. And I'm going to the equivalent grounding conductor. So here's the system that you guys are facing. Let me write the name of the panels. The name of the panel is going to match the panels that you guys have. This will be my service panel. This boy will be my receptacle panel. This will be my lighting panel. And this will be my mechanical panel. Mechanical panel. Very similar to what you guys are doing. You're faced with this situation, my friends. And you're supposed to size the following. We will size the following for this system. I will size number one. I will size right in here. That will be number one. The service panel. The service panel itself. Number two that I'm going to size is the overcam protection device for the panel. Number three is going to be the service conductor coming to the panel. Number four, you can see, guys, we're going in order here. Number four is the neutral, because the neutral is going to be slightly different. Number four. Number five, I want the bonding jumper. This bonding jumper is, I'm going to call it number five, the bonding jumper. Number six is this equivalent grounding conductor. That's my number six. And so this is for the service. And I'm also, guys, going to do it number one, which is the panel size. I need that. I call this one also number one. Remember, for each and every one of these panels. And the overcap protection device. This overcap protection device is also going to be number two. That's feeding the panel. And number three is the conductor. Same thing, the feeder. And number four. It's going to be the feeder. So feeders and neutrals and so forth. So that's what I'm trying to find. Okay, so does that make sense? We have a panel, a service panel, and we need to size, and from this surface panel, we're feeding typically guys receptacle panel, lighting panel, and mechanical panel. Most commercial building, almost always, they take this format, and we're supposed to size all this system. Any comments, guys, before we move on? Any comments? This is going to be similar to the project that we do, as well as we're going to be testing you guys on it. Okay, let me go get you the information that you need to size. So this is how the building is going to look like. And let's go find information to size these panels. When Michelle Cooley guys come to us right here, and they always talk, when you walk into any commercial building, the first thing you're going to size is through a main panel. From that main panel, almost always you tie 3 more panels. Almost always for a big commercial building. The first one goes feed all the receptacle. The second one goes feed all the lights, and the third one goes and feeds all the mechanical equipment. Does that make sense? Feeding all this stuff. Any comments, guys, about the given? So that's how so our job, my friends, your job and mine, is to size this system. To size it. So what I'm going to do, guys, with you, I want to size the main. My goal is to size the main and the receptacle panel. Then homework for you will be to size the lighting panel and the mechanical panel. That will be your homework. You'll see how when I go over it, it makes a lot of sense. Your homework will be lighting panel, receptacle panel sizes, and mechanical panel. Okay. Any question, guys? I want to remind you this will be PDF, so that image you're gonna have it. Can I switch to the second screen? Second screen? Yes. Okay. So let's go to next slide. Here's the given. I'm going to go directly into what's given. And I want you guys to go right into it. I have A. The first thing that's given is receptacles. My receptacles, I hired Jamie, and Jamie installed 500 receptacles at 20 amps at 120 volt. That's the first thing. When Jamie start throwing these receptacles, end up with 500. Okay, then so I'm going to call this is A. I'm going to call this is A1 in this case. A1, my friend Kerry had, what do we call them? These multi-out assembly. We're going to throw a couple of multi-out assembly. I have multi-outlet. The multi-outlet, guys, simultaneous or continuous or simultaneously used. Simultaneous, I have, let's just see, what did they have, Chad? I have 80 of them, 80 feet, and non-simultaneously used, I have 60 feet, okay? So that's my receptacles. I call it load A. Load B, guys, I have lighting load, my lighting load, and we hired Jeff to do the lighting, and Jeff installed the following: 300 fixtures these are 300 fixtures at 1.65 amp at 120 volt. So 300 fixtures, and you install them at this amps and this voltage, right? That's what we typically do. Then you went to B1. I call this is B1 because still lighting. But these are all lights. I have a show window, and my show window, guys, have 40 feet. And then track light, P2, track light, and my track light is 100 feet of a track light. And B3, I have sign for the building, and my sign is only one sign, not two for sign. And the last thing in the B is B4 is parking lot. Parking lot lights. For the parking lot lights, we hired Zach, and Zach installed 6 fixtures. Each one of them is 400 volt amp metal halide that burning at 120 volts. Any question, guys, about the given? These are all the loads that we have, lighter receptacle. Now, Kerry, I used A to represent the receptacles, and I used B to represent the lights. B, B1, B. Wherever you see a B, it's related to light. Can you guys see why am I using B, B1? If you have B and B1, 2, 3, all the B's, Jeff, my friend, are related to lights. The A's are related to what? Receptacles. Just to kind of slip a little bit. Yes, sir.
Just understanding the math. Parking lots are usually going to, for the whole lot, it's only going to use like 3 amps for the whole lot at a time.
Parking lot, I'm using 6 fixtures. Each one of them is 400 volt amp, and they're burning at 120. This one, I think you're confused. Here, I'm using 300 fixtures. Each one of them is sucking 1.65.
Massively underestimating how much the parking lots are taking.
Oh yeah, parking lot takes good juice.
The pictures are
Volt amps. This one, I gave you this one in volt amps. Can you guess? I gave you in volt amps.
3 amps.
Yeah.
I was thinking it was 3 amps the whole thing. But there's 6.
No. Okay. Can I switch to the second one, guys? Jeff? Okay. If you guys follow up with me and you do the Excel sheet that I did you will never go wrong with load calculation. You really would never. For a commercial building. We're going to use, Aaron, we're going to use the same calculation for the industrial building. The only thing we're going to add next time is manufacturing floor full of machines. We're just going to add machines. Another step that says owner-owned machines. That's all. The same steps that we're going to do here, we're going to do in the next project, except we're going to add big chunk of machines that sucking current in the manufacturing floor. You don't like my language?
No, I the buildings that I worked in.
Did it? Yeah.
That sucks the big
You,
units, yeah.
you got it.
There was a lot more volt amp for some of them built.
Absolutely. Okay, C. I use C to designate heat. So I have my heating for the building, guys. We hired Jimmy, and he said, I'm going to use 3 heaters, and they're going to be sucking 115 kW, and they are 208 3-phase. Remember, we're a 3-phase system. 208 3-phase system. By the way, unless I tell you it's 3-phase, the loads are single phase, right? So it's very important for calculating the neutral later on to know is it single phase or 3-phase. That's why I put the voltage, if you remember, next to them, because you don't know.
They're doing 100. You said 115. Are they doing 15 or 115?
15 kW. Did they say 115?
Yeah. But 100.
Oh, I'm sorry. 15 kW. Chiller. I have a chiller under this C also. My chiller have 3 chillers, and I have an amp of each one of these chillers is 82 amps, each one of them, and the voltage is 208, and it's a 3-phase. So I bought a chiller with this information. So it's a 3-phase chiller, 82 amps, rated load amps, and 3 of them. Cool? Step D. So this is the given. Step D motors. Step D motors. So we hired, whom am I going to pick on? Adam, and Adam decided to use the following. Adam, he bought 8 handling. So Adam installed the air handling unit. This is air handling unit, and he bought 2 air handling units. Each one of them is 20 horsepower, and they're burning at 208. And it's a 3-phase system. Remember, this is 208 3-phase system. Then Zach decided to throw another pump for the mechanical equipment, and his pump, I have 2 pumps, and these babies are running at 10 horsepower. Same thing, 208 3-phase. You will be a fool to use any machine that's not 3-phase if you have a 3-phase system, right? So if the pump, should I use a single-phase pump in a building with 3-phase pump? If you have a 3-phase system, you will be fooled to use a single-phase equivalent. Why? Because it's efficient, very efficient. Can you use them? Yes, but is it a good idea? No. Okay, last but not least, E. So I have an E, guys. E is kitchen equipment. Kitchen equipment. For kitchen equipment, I have the following. I have a water heater, and this boy is burning at, I have 3 of them, and they are burning at 5 kW, and at the following, 208, 3-phase. Remember, dishwasher, my dishwashers are, I have 3 of them, and they're burning at 2 kW, and all these dishwasher, I'm running them 208 single phase though. They're running them at 208 single phase. I have a range. These are all kitchen equipment. My range is, I have 3 of them, and they're burning at 10 kW, and the voltage for each one of these is 208 single phase. And the last thing is heater booster, a heater booster. They use it in the kitchen, and these boys also 3 of them. I like the number 3, you can tell. 3 kW, and at 208 single phase. Okay, these are all the equipment in this building. It boosts the temperature before you use it. It heats the water to boost the temperature of the water, raise it up. I'm sorry, Zach, did you say something? Like heat lamps. Okay, the last thing, guys, you need the square foot of the building, right? The last thing, what's the square foot of the building here? So let me see if we can put, I don't think, I'm going to write the square foot of the building right here, so you guys can put it right next to the diagram. It's an office building. This is an office building, and it's a 50,000 square foot. And the system that we're using, so this information is very important. We're using a system of 208/120 volt, 3-phase, 4 wire. Very important, guys, to specify what type of system you want to power this building, because I could use 480 and it changes the whole calculation. So this is right, if you guys put it right next to the one line diagram. Okay, you're going to see it's going to go fast, guys, the calculation, because you guys did it with math. Most of the calculation goes fast. It takes longer to write the information than to do the calc, really. Okay. Okay, the only thing I need help with, because I modified it, I added here. So otherwise I do have them. Any question, guys, about the system? Can I switch and move on to what's important in life? Okay, let's go. The first thing I'm going to do, guys, is I'm going to find the receptacle load, the receptacle. So I'm going to call A. Remember A, oops, this is not an H here, this is my A. I'm going to use A to calculate the receptacles. So for A calculation, I'm going to write here receptacles. Remember A was what? This receptacles. For receptacles, I'm going to do 2 calculations. Because remember how we did it yesterday? We did 2 calculations. The calculation number 1, I'm going to call it A1. This is my calculation 1, A1. So you take 1 volt amp, 1 volt amp, multiplied by, what's the square foot of the building? 50K square foot. What do you get? You get 50 kVA. Circle this one. This is the calculation for the receptacle based on the code. Based on the code, and I'm not going to write the code for these guys, but for this particular one, is 220.14K. Remember that code? 220.14K. That's calculation number 1 that you need to do. K is the one, is K is the one that tells you guys to do 1 volt ampere square foot, and I is 180. Yeah, I think I is 180 and K is for the 1 volt amp. I know it might be written the same step, but they're related to two different things. Okay. So that's calculation 1. Now calculation 2, I'm going to call this one A2, guys. We're still under A. A2. And this one is based on NEC at 20.14i. Is the I the one that says 180, right? Can somebody, okay, just want to make sure. 180. Okay, based on this, here's what we're going to do. The code says you're going to take the actual, this is called the actual, which is what they designed for. How many receptacles did Jeff put in this building? 500. Multiplied by 180, what do you get? 90 kVA. 90 kVA. Okay. But keep in mind, guys, there's also a multi-outlet assembly. Remember that multi-outlet assembly? 90. Okay, so these are for actual. A2, I'm going to call this one A3, guys. Can somebody give me the NEC for the multi-outlet assembly? 14 H, thank you. For 14H, this is the multi-outlet. Do you guys remember what the multi-outlet says? How many of them do I have? Simultaneously or simultaneously used or continuous. Is that a continuous? We call them continuous actually. If it's continuous, how many of them we put continuous? Anybody remember?
1 foot per 180.
Yeah, but we put 60 of them. 60 simultaneously or continuous load. Multiply this one by 180. Divide this one by 1. Anybody knows why 1? If it's continuously used or simultaneously used, I use simultaneous, should be continuously used. 180 volt ampere square foot. So you take the number of feet divided by 1, multiplied by 180, and I need somebody to give me the math. I don't have the math for this. And while you guys think about it, I'm going to take the non-simultaneously, non-continuous. It was the non-continuous was 80. You divide this by 5 and you multiply it by 180. And I need somebody to give me the answer for these, please.
10.8K for the first one.
10.8 kVA. Second one. Any second?
2.88K.
How much?
2.88.
2.9 kVA. Do I have a second, guys? Second. Adam, did you do it? Yeah, I'm doing it. Okay, thanks. You see how that's what you guys did with the Excel yesterday. I know, Jamie, you asked me about the numbers. Everybody can recognize the 5 and the 1. Why 5, 1, 1? Divide by 1 because if it's continuous, 180 for every 1 foot. Divide by 5 because non-continuous, 180 for every 5 feet. I'm going to make a step. I'm going to move. Now I'm going to add them up. I'm going to add them up so I can apply the demand for them. So right here, I'm going to say A2 plus A3, right? These two steps. Can you guys add them up, which is 90K plus 10.8K plus 2.9K. Who's my favorite friend who's going to give me the answer for them? Add them up. Because I need to apply the demand. I added only the A2 and A3, not the A1. We need to compare with the A1. Adam? 113.7. 113.7. Any second? Second. Thank you. K, V, and A. So we add them up. Everybody knows why we need to add them up. We need to apply the demand factor. Yeah? 103 point.
103.7.
Oh, okay, 103.7.
Way to go, Adam.
103.7. Sorry, man. 103. Okay, we're not gonna lose each other's after 1 kilovolt amp, guys. Come on. That's nothing. 103. Was it 10? No, it was 10 actually. 10. No, that's your house. That's the load of your house. 10 kW is a house. You just added a house to the load. Okay. Can I flip to the second page? Flip to the second page. Okay. Anybody can guess what I want to do next? Just give you a heads up. I want to apply the demand factor on the blue and then compare the outcome with the 50K and choose the largest. Okay? All right. So let's go to this step. Remember, we're still dealing with the A's, which is receptacle and all this good stuff. This one I want to say apply from table 220.44 demand. We're going to apply the demand. What was the number again that we came up? 103.7. Okay. The first thing here, don't you mess with them. Anything higher than 10K, so you take 103.7 minus 10. You multiply this by what? Multiply by 0.5. Oops. Wow. Okay, let's adjust. We have 3. All right, let's go one more. This is my demand. I have 103.7K. The first thing here, sacred KVA, leave him alone, right? Then you take the 103.7 minus 10K, and this you have to multiply this by what? 0.5, and then add him up, right? I need two gentlemen to do that one. Give me an answer. And that will be the demand for this step. How much? 50. 6.85.9. 56 or 46?
Yeah, but you had the first.
You had the 10?
Oh, total, yeah.
Yeah, total. I want the total. KVA. Okay. Now I want you guys, do me a favor. I want you to highlight this and put 2 stars next to it. This is the demand for all the receptacles. Make sure you put 2 stars. This is demand for all your receptacle load. Everything receptacle, that's your demand for it, right? No, I'm sorry. We still need to compare it yet. No, don't do that. I like you. We still need to compare it. The last step that we do is choose largest. Choose largest of demand or code or NEC code. Okay, what was the NEC, Cam? 50? Was it 50, the NEC? So I have 50, 56.9, very close. So which one do you guys want to use? So can I say here largest of 50 kVA or 56.9. So the largest of these two, which one do you guys going to think? 56.9. This is where you're going to highlight this boy, kVA. You're going to start that boy for me. And this will be the number, the complete actual last number that you're going to use everywhere else in the calculation. Can you guys write yourself a note? I put these 2 stars. This is means after demand, done. All the A's are done. That's the number that you're going to live with. Now, Darren, since you're my favorite, you think when they size the receptacle panel, don't you think, are they picking on you now? Okay, since you are not my favorite, do you think when they size the receptacle panels, I'm going to be losing the same load, that number? Yeah, that's because all these are receptacles. So that will be used for the main panel as well as for receptacle panel. Okay. Can I jump, guys, into a different load? These are the A's, all the A's. Can I go to the B's? May I go to the B's? Okay, let's go to the B's. This is my A's. B's, let's go to B. B, guys, lights. B is lights, right? The first thing, and this is coming from table 220.12, 220.12. Okay, the first calculation you need to do is take 3.5, multiply this one by what? 50K square foot. And here's what I did here that I didn't do in your sheet. I don't want you to get confused. This is what we did in your sheet, except now I'm adding the continuous load directly to right here. So I'm going to add continuous load right in here. That slightly different than what we did in our sheet, 1.25. I added the 1.25 right to this step, right to this step.
Add or multiply?
Yeah, I'm sorry, multiply. Multiply it directly to this step. Okay? Now you could add it, multiply at the end, or you can multiply it right here. So then what's my outcome for this step? My outcome would be 219. 219 kVA. Okay, so that's for the general lights. That's for my general light. General light from NEC. The second step, guys, you need the actual light, right? There's general, there's NEC. Let me say, I should probably put this one like this. This is NEC. NEC calculation, and right, and the second right underneath it is actual. Okay, for actual, anybody remember what, who designed this building? Who is Joe? Joe decided to put 300 fixtures, right? And each one of these fixtures was sucking 1.65 amps, and the voltage was 120, so that's the volt amp. Can you guys see I'm calculating the volt amp? And because it's continuous load, what do you do? 1.25. Okay, can everybody give me a thumbs up? We understand where the 300 came to be. That's actual fixtures. Anybody understand where the 1.65 came to be? The 1.65, Zach, when you go to the ballast and you read what's on this ballast above, that's the amp that each fixture is going to suck. Okay? Everybody understand what the 120? What's the 120? The voltage that this fixture is going to be operating. And what's the 1.25? The continuous load factor. Right? Applied. Okay, so if you do the math here, you're going to end up with 74 kVA. 74 kVA. And Hala Evan is online. My sister, and then you keep popping up here. Okay. Any question, guys, about the general lights? This is general lights. The general lights. Okay, now, I want to add this one just because lighting demand, for this one, if you guys go to table 220.42, it will tell you the demand factor is 100%. What does that mean? It means all these fixtures that you did, do you need to apply demand like receptacles? Do you need to cut them by anything? 100%. Leave them alone. I didn't write this step for you guys because it didn't do anything. But you need to understand, when you do the lighting calculation, the actual, you have to apply demand to it. Go to the table, see if there's any demand. We know if you go right now to this 220.42, if that was a house, remember if it was a house, there is a demand. But for commercial building, the demand is 100%, so it really doesn't alter the calculation. The last thing for this step, guys, is choose largest. Choose largest of the actual, which is what was my actual? 74K and 21.9K. So it doesn't take a genius to discover that the largest is what? kVA. and you highlight this, you put stars next to it. Well, we're gonna be, and that will be it for this step. That will be it for this step. For the actual lights. And you just put the stars next to it. So it tells you that this is going to be the one that you're going to be carrying. For the general lights. Any question is about this? That's your B, your general light. Now remember, for lights, there's other non-general lights, track lights, and all this good stuff. Okay, let me know when I can jump to the other types of light. This is for your general light. Okay, whom am I going to go? Andrew, I didn't pick on you today, bud. Can you guys, this is what you didn't do in your steps. The actual, remember how we made another sheet for the actual? We said we're going to compare them. Can you, Andrew, can you assure me that you understand that we do the two calculation and we pick the largest? Cool. And I know with the Excel it does, because Excel it jumps around. You don't see the actual math behind it. Hopefully with this, kind of sticks in your mind. If you guys get it now, we might let you go in the spring and see if enough is enough with Chad. Is that good? Remember, I'm not under oath, right? I always tell my wife, if you want the truth from me, what do you do? Put me under oath. Okay, B. I know it's Friday, guys. So this is B1. You guys remember what B1 was? B1 was the show window. B1 was my show window. Now, Jeff, my friend, this is your reference, 220.43a. Please check me on, when I write the references, sometimes I write them wrong. So if I made a mistake, please, I apologize in advance. There were 200 feet of the show window. And the code says, for the show window, and I'm sorry, there was 40 feet of the show window, 40 feet, right? And multiply it by code 200 volt amp, and multiply it by 1.25, and we all know why 1.25, continuous load. That will give me 10 kVA, 10 kVA, and highlight this and put stars next to it. This is the demand for the show window, right? Nothing, you don't cut it by anything, you just continuous load. Okay, so that's B1. Let's go to B2. What was B2? If you guys remember, B2 was a track light. Track light. And that was 220.43b. I trust that you guys will verify that it's 220.43b. And how many feet of them? 100? I think I gave you 100, right? So here's 100. And the code says for every 2 feet, you allocate 150. Okay, that's what you're gonna. So for every 2 feet, you allocate 150. How do you do the math? You take the 100 feet, you divide it by 2, and you multiply them by what? 150. Everybody can see what it did. For every 2 feet, you allocate 150. When you do the math, you take the length of the track light, divide it by 2, and multiply it by what? By 150. And then because it's continuous load, what do? This is volt amp, and because 1.25 because continuous load, so that will get you 9 kVA, and you circle that boy, and you star it, and that will be your baby. That will be your baby. Any question is straightforward, no? The B3, what was B3 again? Sine, thank you, sine. Sine, here's your reference, 220.14f. This is a grade that nobody will get, hopefully, in the class, F. And articles, I think 600 also. I think I had the article for you about the sine. Anybody? I think it's 600.5. You might have to verify these. If you go there, I know the math is right, but the articles, you might have to verify it. it tells you you need at least one sign. Unless they tell you otherwise, what do you need to do? One sign, multiply this sign by 1200 volt amp, because the code, I think 600.5 says so, and then multiply it by 1.25 because continuous load, and you get yourself a 1.5 kVNA, and you add, and this is the step that you're going to take all the way for this light, for these lights. Any question, guys, about the lights? That's it. These are all the lights. Now, you could add all the steps together and make a complete big chunk of load. Let's do that. I want to say, thank you. I forgot, that was in my thing. Thank you. B4, did you write 2 here or 3? Why do you guys keep writing on my board and you don't tell me? Okay, that would be B4, right, Kerry? Yeah. B4, thank you. Parking lot. Light. What was the number that I gave you guys for it? How many of them? I have 6 of them, multiplied by 400, I believe, 400 volt amp. Now, I could have given you the amps and the voltage here, and you do the math exactly like the one that we did inside the building. I multiply this because continuous 1.25, right? At night, you run the parking lot lights more than 3 hours, right? At least most of us. And I need somebody to do that because I don't do the math. I did not do the math for this. 28 kVNA. Do I have a second? A second? Yes? No?
3,003 kVA.
How much?
3,000.
3,000 kVA?
No, 3,000 volt amps, so 3 kVA.
3 kVA. I see. That shouldn't. Okay, I should have looked at the actual 3 kVA. Okay, sounds a lot, 28. But I'm not thinking. Okay, 3 kVA. We multiply by an extra 1. Not a biggie. Not a biggie. Okay, so start that boy. All right, so I'm going to add one more step for you to make it easier. Now, all the lights, I'm going to add them up and have big chunk load for all the lights, right? So here's what we do. And you don't have to do that one. So I'm going to say this is for step B. All of the B's, which is lights. For lights, I might have to. I have to go to a different screen. I really want them in the same screen so I can. Well, we can't use it unless this is here. That's the interlocking. Slide it. Okay, let me go to the different screen, guys, and I'm going to add them all up. Okay, so I want somebody who's my favorite. I'm going to say B, all lights. So for basically lights. Okay, so that would be B plus B1 plus B2 plus B3. Do we have B4? Plus B4, all of them. I need you guys to give me the numbers, please. The first B, what was B?
219 kVA.
319, 219 kV, 219 K plus, what was B1? 10 K plus B2? 9 K plus 3? 1.5, yep, K plus 3 K equal? How much?
242.5.
Second? 242.5. Do I have a second on this? Okay. A third, because this is very important. Do I have a third?
Yep.
Okay, thanks. Oh, the same person? No, you can't be the second and the third at the same time, man. Okay, because I added all of them together, guys, because I added them together, all of them as a lump sum, you might not need all these. It might confuse you, the stars that we put here, because stars mean carry them. I want to go get rid of my stars. I usually don't do that step that I did with you, but this time I think it makes a lot of sense to do it. Okay, so I got rid of the star. Did you see what I did? Only for lights. So I got rid of the stars because I added them all up. So all the lights, everything light was lump summed in one big step. Everything receptacle was lump summed in one big step. Does that make sense? Okay, so that's if you get rid of the stars here for all the B's, guys, like I did, so you don't get confused when we go back to carry them, to size things. Here you go here, right? There you go. Okay, I'm going to flip here into, where do you think we're going to go now? A, B, what comes after B? D? Did somebody say D? Okay. A, B, we got all the signs, we got all the steps. We're gonna do C. So what was C again? C is heating. Heating. So for heating, guys, your reference is 220.51. Can you guys add this one to 220.51? 220.51 for your heat. And remember what the heat was? It was three of them multiplied by 15 kW, and you take it 100%, and that will get you 45 kVA. Okay, that's for the heat. Let's go to the second one. Second one is I have a chiller. Chiller, that's the cool. Everybody can write cool here next to the chiller. Cooling, okay? Your article for the cooling will be 220.50, 220.50, and also the 440, article 440 talking on this. These are your references. How many chillers? I had 3 chillers. Multiply the chillers by the amps, 82. Multiply this by the voltage, 208. And multiply this by 1.73. I want somebody to tell me why 1.73, Chad. Thank you. 89 kVA. If you guys start telling me that, we have just arrived to the commercial industrial. Okay, cool. The last step for this is that, remember, there's a demand on the heat and the cool. So step D, there's a demand on it. You choose the largest of the two. So I have 89K and 45K. Aaron, which one do you think is bigger? It's a dumb question, isn't it? Not for you, but you choose the largest, right? So you grab the last one from NEC 220.6. That's what this step is. If you go there, it tells you choose the largest of these non-simultaneously used equipments, right? They're not going to be used at the same time.
How come we didn't multiply the heater by 1.7?
Very good point. You only, because the code says if you go to 220.51, it tells you take them at 100%. Even though they're continuous load.
Well, 1.73 is 3-phase, and the heater's a 3-phase.
Yeah, but remember the heaters were given in what? In kW. The chillers were given in what? In amps. Right? Very good point. If I give you the amps of the heaters and the voltage, then you do the same calculation. So when you multiply the amps by the voltage by 1.73, you get what? So this step has been done for you. Very good point. Very good point. Okay, so choose largest here. Choose largest of heat and cool. Okay? So when you guys do that, it doesn't take a genius to discover that the step is here K, V, and A. This is the one that you're gonna star. You're gonna put a star right next to it, which means you're gonna carry this one where? Downstream. You're gonna be carrying it downstream, right? So that's step C. Does it make sense when you do it slow down and instead of all these Excel sheet and I hopefully carry this with the sheet will get you there. Huh? Yeah. Now what's wrong with this one versus the whiteboard? I mean, is that am I going too fast on it? You can.
Well, Brian's not here, so you don't have to worry about it.
Okay, let's go to D, and then I'll give you a break. I'll do D and give you a break. D. Let's go D, but that board. D. So D was motors, guys. Remember D? D is motors. Your article for this one is 220.50. If you go to 220.50, guys, it will tell you the following. Now remember, the motors were multiple loads are motors. The first load was air handling unit. The air handling unit, I have how many of them do I have? Well, before the air handling unit, it's a 20 horsepower at 208 volt 3-phase, right? So you need to take the the first step you take to take the 20 horsepower, take it to table 430, thank you. You're going to take it to 250 under 208, and you find the full load current, which is, I found it 59.4 amps. First, you need to find the full load amps, right? So you take the 20 horsepower and find the full load current for it. Cool? Straightforward like we did before. So that's going to be under the heat. You step 1. Step 2 under the air handling unit is you're going to take how many do I have? 2 air handling units or 1? 2 air handling units. Okay. Okay. Yeah, I have a pump too. Okay. Now I'm going to do this one slightly different, so I don't want you to get confused. So now, how many pumps we have? 2. Which one is the largest load by looking at the air handling unit and the pumps? Air handling unit, because it's 10 horsepower. So here's what I'm going to do in one step. I didn't do it, guys, with you. In one step, I'm going to choose the largest motor right away and multiply it by 1.25, which would be one of the air handling units. So here's what I'm going to do. Number 1, I will multiply 1.25 times. The first thing I want to do, which is 59.4 times, what's the voltage? 208 times 1.73, okay? That's motor number 1, plus motor number 2 is 59.4 times 208 times 1.73. Only an engineer will do something like this, okay? Equal. See what I did? I took the largest motor, which happened to be one of the air handling unit, not the pumps. We're doing the pumps yet. And I added 25% to them, and then I added the other air handling unit to it. So I just put them in one step, and that would give me 48 kVA. Anybody came up with 48? 48 kVA. 48 kVA. So this one is for my air handling unit. Let's do the pump. I have also pumps. For my pumps, they're 10 horsepower at 208 3-phase. So we're going to do the same thing, guys. Take the first 10 horsepower. You're going to take it to the same table, 430.250 under 208. You're going to get how much amps? You're going to get 30.8 amps. Okay, then I'm going to do the second. So this is the pumps. Then I'm going to do, here's what I want to do. I want to do the 2 here times okay, times the amps, 30.8 times the voltage, 208 times times the 1.7, 1.73 the factor, and that will get me a 22 kVA, and you're gonna star this, okay? Cool. I'm gonna just put one star next to this and one star so I can know these are the ones I want to carry. Okay. Let me repeat myself because that could be confusing. When we did it in Excel sheet, this is what we did, guys, in Excel. First, we added them, and then we took the largest motor and add 25% on it. But you can do that. What I did here, the calculation, I took the first motor. This one is for the largest motor. Everybody can see that factor for the largest motor. So I took this multiplied by the largest one of the largest two motors, one, right? And then I added the second one to it. Then all the two pumps I added together. Now I'm going to add the total for the whole step, all of them together. So have a total for all this step. So I'm going to call this as, I'm going to use, so total motor load, right? The total, which would be equal what? 48.
That's 70 kVA.
Which one?
Add them together.
Yeah, I'm sorry. Yeah, plus 22K, and that will give me 70 kVA, and this will be the finalist answer that you're gonna do. That's all your motor load will be lump summed as what? Big chunk of 70K. 70K. Does that make sense? That's yes, sir.
I think I missed what you're saying. The reason you circled that squared 1.5 is just because that was the largest amp.
That was the largest amp motor. Yep.
And now the rest of them are small motors.
They're all added 100%. Right? Is
And
the
then
second.
the pumps too are under the same.
Yep. They're all motors.
But we're bigger than you could have.
Yeah, because look at the amps for this one is 30.8, the amps for this is 59. Good point. But ultimately, can you see how, and I don't know if you can see, I sliced it a little bit deeper so you can see how the math is going. But what I did is took the largest motor, multiplied by 1.25, I added the volt amp of all the other motors there. That's what I did. Okay, do you guys want 5 minutes? Cool. Let's do 5 minutes. And then we'll switch to step. What comes after D? F. We don't want to go to the F though, we said.
No.
Oh, man.
15 to 30, or actually, and nobody takes the second 15, so it's only half-hour lunch.
Yeah. Okay, guys, if you don't mind me bringing you back to E,
Hour down for trust me, dude.
let's do the kitchen equipment. Kitchen equipment. Kitchen equipment. Did I spell it right even? Close.
MEMT.
MENT. I think I'm done today. There you go. Okay. You're gonna go to for kitchen equipment, guys. You're gonna go to 220.56 and table 220.56. There's a table and there's an article, and it will tell you if you have more than 3, I believe. Did we say 3? More than 3, you cut it by 60. There's a table. Can you guys go to the table and see what? More than 4, you start cutting them. I can't remember if it's more than. If you go to 220.52 because that's a new table. 220.
Multiply 3 or more pieces of equipment by the table.
There you go. 220.50. 56. I said 56. Okay. So kitchen equipment, other than dwelling. Is this a dwelling? No. So that's applied to it. All the kitchen equipment, up to you start cutting after 3, right? 3 or more you start cutting. So how many room do we have though? let's go write the stuff that we have. So here's what we have. For this one, we have a water heater. For my water heater, guys, I have 3 of them, and I'm going to multiply these 3 by 5K because each one of them is 5K. And the second one, I have a dishwasher, and I have 3 multiplied by 2K, and I have range, and this boy is 3 of them. I multiply these by 10. I like the 3. And booster, heater booster, or booster heater, 3 times how many? 3 kW. And I'm just going to put the voltage for the, so I'm going to put the voltage for them, guys, for a second here. I think that this, which one of them was 3-phase? All of them. Okay, give me the 3-phase. The water heater was 3-phase,
And everything else is single phase.
208, and everything is 208, single phase, 208, single phase, 208, single phase, and 208, single phase. It doesn't play any, it doesn't do anything here for you, but when you do the neutral, it does. That's why right now it doesn't mean anything, but when you do the neutral, it does, right? Okay, so how many equipments do I have? I have 1, 2, 3, 4, 4 times 3, 12 equipments. Everybody knows that we have 12 equipments, right? 12 equipments. So this is the first thing you need to do. We're gonna add them up. Can you guys add them up? If you add them up, you're gonna end up with 60 kVA. That's step number 1 for all this. Step number 2 is we need demand. Demand. How many equipment do I have? 12 equipments. 12 equipments. You take it to this table, table 220.56. What's the demand factor for this boy? 65%. Everybody can see that the demand for 12 of them. Why 12 of them? Everybody can see that these are all, when you add them up, you come up with what? 12. Can you guys see where the 12 came to be? Demand for 12 equipment from 220 to 56 get you 65, right? Adam, did they do something wrong? Is there anything?
No, I thought it said AWH up there, but it's a star.
That's my star. It's confusing you. Sorry, what? We'll unstar it.
It's not hard to confuse me.
Okay, here you go. I'm just putting. Okay. And then you take the 60K. The last step that you do is you take the 60K and multiply it by the demand factor, 0.65, and that will get you healthy 39 kVA. This is the one that you're going to star, and this is the one you're going to carry for this step, right? That's all the equipment for the kitchen as lump sum load of 39 kVA. Can you guys see the phase didn't play any role here because we're given the kVA. When we do the neutral, I want to say a few things about when we size the neutral becomes the 3-phase versus single phase big deal. We're done with the calculation. Now we're going to go add them up in a second here with my friend. I need 1, 2, 3, 4, 5, 6 rows. Okay. Any comments, guys? Any question? Aaron, let me know when you're done, my friend. Okay. I can wait. No big deal. Good? Okay, good, everybody? Okay, now I'm going to add them up. Now, when I add them up, here's what I've done in the past, guys. I would like you... I need 1, 2, 3. Okay, do me a favor. I'm going to make a table of 9 rows, 9 columns, and 1, 2, 3, 4, 5, 6, and 6 rows. Okay? So you're going to go with me here. This is how we're gonna handle this one. So I'm gonna say 1, 2. Okay, 1, 2, 3, 4, 5, 6, 7. There's 1, 2, 3, 4, 5, 6. Oops, where's the 6? 6, 7. I'll show you how that really comes handy in a second. Okay, so 1, 2, 3, 4, 5, 6, 7, and down 8 is good. And then I need columns 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 columns. Starting from here. Oops. No, starting from here, Chad. Is 1, 2, oops, 3, 4, 5, 6, 7, 8, 9, and have an extra 2. Okay, so you're going to see why I'm doing it this way. The first column I'm going to call here my load. I hope I can type it here, load. Here's my load. Then right above my load, right? My load, I need my SP panel. I'm going to say the phase and the neutral. Right next to it, it's going to be my receptacle, receptacle panel, and it's going to be the phase and the neutral. Right next to it, it's going to be my lighting panel, my phase, and my neutral. And right next to it, it's going to be my, oops, I'm running out of room here. What did they say? I have my service receptacle lighting panel. I might have to add one more. There you go. You're going to see what I'm trying to achieve in a second here, because I have multiple panels. So right here, what do you guys think after that? Remember that lighting panel? I have my lighting panel. No, I did good. I have SP, RP, LP, MP. I'm good. I don't know why I did that, Chad. Why did you got confused here? So I have SP, RP, LP, and the last one is MP. I have MP, and this is my phase, and this is my neutral. Cool? And I just actually have, and if you have another panel, you can keep adding them. Okay? That was good. I just got confused for a second. Okay, look what we're going to do. Now, this is going to size the whole system for you in one step. The whole system in one step. Everything. Every one of them. So, let's start by putting the load. Load number 1, A. You guys remember load? The first load is A. Okay. So, A, under the, A was the receptacle load. It was, what was it? Receptacle load altogether? Can you guys go get me the receptacle load? The total for A. The total for A. Because I think it's different than what I have here. What is it? 56.9. So this will be a 56.9. Do you guys think this is, since this is a receptacle, all of them are going to be sent by the neutral? Right? Yeah, because they want one. So also under the neutral is going to be 56.9. Now, this is receptacle panel. Are these going to be fit from the receptacle panel? Yeah, the receptacle load. So what do you think this under here is going to be? 56.9. Are they going to also seen by the neutral for the receptacle? Yep, you got it. 56.9. Do you think they're going to be seen by the phase of the lighting panel? Big fat 0. Big fat 0. Big fat 0. Big fat 0. Can you guys distinguish between the 0 and the phase? Now it's going to. The red ones are zeros. The top are phases. Okay? Can you guys see what I'm doing here? I'm taking the chunk of load. All the loads are going to be seen by SP, the service panel, but some of them are going to be seen by the other panels, and some are not, right? Okay, let's go to B. Who's going to give me B? The B load. What was the B load again? Lights. All the lights. The total demand for the lights. 242? Was it 242.5? So it's 242.5, and it's also 242.5. Now, do you guys think it's going to be seen by the receptacle panel? Nay. Nay for the neutral here. Is it going to be seen by the lighting panel? Yep. 242.5, 242.5, 0 for mechanical, 0 for mechanical. Can you guys see what I'm doing? I'm picking the load first under, all of them are going to be seen under SP. Then I'm allocating it to a panel too. Allocating the same load to a panel. The same load to a panel. Now, in one sheet, you size the whole system. One sheet. Okay, what's after B? A, B, C. What was the C load? C was the heating and cooling. How much the demand for the heating and cooling? 89. 89. Now, remember the heating and cooling, all the heating and cooling were what? Three phase. Remember? All of them are three phase. So are they going to be seen by the neutral? For your heating and cooling? So what do you put here? 0. Okay, now receptacle panel. Are we putting anything on the receptacle panel? No. How about the neutral? No. Are we putting anything under the lighting panel? No. No. Now go to the mechanical panel. Are we putting things under the mechanical panel phase? For the mechanical equipment? Yes. All these are heating and cooling. I'm going to put them. You really have to decide. Are we putting them on the mechanical panel? Yes, because they're mechanical equipment. We're going to put them on the mechanical panel. So what do you think is going to be here? 89. Now what do you think the neutral is going to be? 0. Cool? Can you guys see what I did? Because the reason why the neutral is 0 everywhere, because they're three phase. They don't contribute to the neutral. Okay, after C, what comes after C? A, B, C, D. What was D? Was motors. And the demand for the motors, the total demand was? How much? 70? 770. Now, just a quick reminder of the motors. We have two motors, 20 horsepower three phase, and two motors, 10 horsepower three phase. Did you hear me saying anything about single phase? So what do you think the neutral here is going to be? Big fat 0, not just 0. 0, 0, 0, 0. Now, all these motors are going to be fit from a mechanical panel. So what do you think under the phase is going to be? 70, 0. Everybody understand why 70 under the mechanical panel? Because I'm going to shift them to a standalone panel. Right? All of them are going to be fit from the main panel, but then after I feed them from the same panel, I'm going to take chunks of them and feed them from separate panel. You guys with me? Everybody understand what I'm doing here? Plugging the numbers. Okay, what else? A, B, C, D, E. The last load, E. Okay, E. What was E? Was kitchen equipment. Okay, let's go back and look at E. First of all, E was the total for E was 39, was it? 39. So this was at 39. Okay, now it's not. I'm going to feed these are all where did it feed them?
No, you got three phase and motor.
Okay, now herd your horses on that one. Now these are kitchen equipment. The kitchen equipment typically we feed them from the mechanical, if it's kitchen equipment, we feed them from the receptacle panel. You really have to decide. I have to tell you, kitchen equipment are kind of special. In a bigger buildings, they feed them from their own standalone panel, guys. But we don't have its own standalone panel. So you and I are gonna make an executive decision. Where are we gonna feed this chunk of load here? I'm gonna feed them from the receptacle panel because I want the mechanical panel to be dedicated for the heating cooling. Okay, so I'm going to grab under the mechanical. Forget about the neutral for a second. Just forget the neutral for a second. I'm going to go with them 39 here. So what happened then underneath all these? Zeros. Okay. Now let's look at the neutral. Let me show you what the neutral are. Let's go back and look at the load. Okay. Here's the loads that fit. The first one, we know for a fact it's a three phase, so it doesn't contribute to the neutral, right? I want you guys to look at the rest of them. They're all single phase 208. Now this is where judgment and right, all of them are single phase two-way, meaning they're just taking two hots, not three hots. Now, how many of them do I have? The single phase ones. I have 9 of them, right? Just the single phase. 3, 3, 3. 9 of them. Does the 9 number divide equally by 3 phase? Right? 9 divided by 3 is what? 3. So that's where you have to use your judgment. So long story short, these, since they are phase to phase, these will be balanced. If they're balanced guys in the system, they're not going to contribute to the neutral at all. Right? So let me just show you how would I connect them. Here's my 3-phase system here. Here's my 3-phase, and coming in here, and here's my neutral. Okay, so what I'm going to do, I'm going to connect each, and they're not using the neutral. Here's my first load is going to be coming in here, my second load coming in here, and the third load coming in here. Oops, not in here. So that's how they're going to be connected, the single phase ones. Okay, and just imagine, there will be 3 of this, 3 of this, and 3 of this. Can you guys see that? That will give you 9. These are the 9 that's going to be contributing the single phase ones, right? Now when you tie them like this and they run, there is no neutral coming to them. They're not running at neutral. Neutral is just stopping right here. It's not running. So if these are connected this way and they're all running, nothing will go back into the neutral. There's no contribution in the neutral. So long story short, the neutral contribution of these loads is what? Big fat 0. And now we're moving further. Big fat 0. Okay, so that's why if you have loads phase to phase, guys, multiple of them, they always balance each other. So the neutral, they're not tied to the neutral. So they will if multiple of them, you can easily assume the neutral is going to be 0. Okay, so what's if they were 120 though, they're 120, they contribute directly to the neutral, right? Okay, so because of this, I hope I convinced you. I'm going to put what? Big fat 0 here and big fat 0 here. Okay? Any questions about this? Okay, now let's go do the math. Did we miss any load though? I don't think we missed any load. So other than I went to town with my calculation here. Okay, so I want you guys to do me a favor. Under each one of these, we're going to do the total. I need the total for each one of them. This will be my total. Let's use this. Okay, what's the total for the phase? Oops, what happened to SP here? SP. Did they move to the other one? I hope I didn't delete it. No, I went back. Okay. S, when you get closer to the edge, this is phase and this is neutral. Okay? All right, so let's get some total. Is this working right? Keeps erasing my stuff. Okay, what did we guys have here? We have 0, right? And we have 0 here, right? 7. Okay, so let's put the math right away. So what's the under the phase? What was the phase right here, please? The total. 497.4. This is coming from here. Coming from here, the neutral.
739.
7. How much?
No, not much. RP. Very last
No,
line.
I'm calculating the phase for SP, the neutral for SP. 299.4. Okay. Now let's do the. I'm doing now the receptacle. The phase for the receptacle.
E should be 39
Which one?
under RP. E.
It's up to-
You got the blue.
Very last phase on RP.
Okay. So are we RP? Okay, for RP.
RP phase should be 39.
39.
No, not total. It should, where the E is, count
0.
line E,
Bottom blue 0.
that should be 39.
Did you guys get rid of this? Okay, thank you. 39. Yeah, because I deleted that. Okay, when you add them up, what do you get? Thank you. 95.5, okay? 4.9? We have to, these are the numbers I'm gonna do the calculation for, guys. 95.9. Point nine. Okay, so the neutral, did we say these are gonna contribute nothing? 56.9, right? All right, so let's go to the lighting panel. What's the lighting panel? Lighting panel is easy. We don't want to even, I'm going to highlight them. The lighting panel is going to be 2 for 2.5 for both of them, right? 2 for 2.5. The mechanical panel, 0 under the phase. And can you guys do the mechanical panel for me? 159. Okay. Okay? Okay. All right. So everybody got these? So I'm going to just group them together. So these will be in one for one panel. These will be for one panel. These will be for one panel, and of course these will be for another. These are the 4 panels I'm going to be using. Okay, let's go size. That's it. When you're done, when you get the kVA for each one of them, now you start the sizing. Let's go size. I want you guys to remember these numbers though, because I have different numbers. I want you to give me, when I'm sizing for each panel, give me the actual number. All right, so now can we switch? Everybody got that one? So get the numbers. The numbers are before we start, because we're going to size everything based on these numbers. Can I have thumbs up, Chad? I didn't make any mistakes. You guys are my witnesses. All right, cool. I don't want to do all the math and find, oops, we missed 10K here. Now I have to calculate. That's what Excel comes handy. All right, so let's go size. The first thing I want to size is the service panel sizing. Okay, for the service panel, you guys remember the first thing we need to size for the service panel? What was it? Let's go back, because it has been a long trip here. Let's go back and see what we're going to do. Now we got all this info. I need to go size all these numbers. Can you guys see these numbers? The first thing was what? So I'm going to remind you, the first thing is the panel size. The second thing is overcompression device. Third is phases. Fourth, neutral. 5 is bonding jumper. 5th is grounding electrode conductor. And we're also going to do all this to all these panels. All these panels. Cool? All right, so let's go back, forward. Okay, the first thing I want to size with this one, my friends. Okay, so panel size. Now remember, we are talking about the service panel. So you take the I. Can you guys give me the total for the whole SP panel phase? 497.4K. Divide by 208 times 1.73. What do you guys come up with? I don't have the answer for this. 2 gentlemen to agree on one answer. Okay? Remember, there's a K. So it's going to be in the thousands, don't worry. 1,383. I need a second on my friends. Second. Nobody's seconding yet? Second, okay. Third. Before we move on, okay, here's the second. All right, so this is the amp. Then you're going to take this one, this number. So that's the first step you need to do. Second step, guys, is going to take the 1383 amp we're gonna take this one to DeWalt. That's where DeWalt comes very handy. And under 3-13. Can you guys go to 3-13 DeWalt and find me? We're sizing the panel, not the overcome protection device, the actual panel. 3-13. I want to remind you guys, go under switchboards or switch gears, 3-phase, not single phase. Okay, my options are 400, 600, 800, 1200. Can I do 1200? 1600. This is where, Joe, your judgment as an engineer. Now, my options are 1200 or 600, actual physical big box. So for 13, so if I go 1200, I'm short what, 183. I probably would go 600, but that's a judgment as an engineer. I can't judge to go down. For me, with me, if you don't know always, what do we go? The safest is what? Go up, always. So what would that be? 1600 amp. So we will buy a switchboard, 1600 amp switchboard. And what we're sizing, Adam, is the copper or the aluminum inside the switchboard. That's what this means. Nothing, just other than the copper. Based on this, the price of the equipment, when you guys do estimating, is going to be completely different if you go from 1200 to 1600. That's why we pay attention to it. Okay, number 2. What was number 2, guys? So we sized the first one. So basically, this is really what my size is. I'm gonna put a star right next to it. That's my size. I go to town with this. I go buy it right now. Okay, so let's go to the second one is over current protection device. Overcurrent protection device, the same calculation, guys. This will be from 240.6. Remember that? You take 1365. You're going to take this boy into 2440.6. And what do you get? 1600 amp. Do we have a 13?
1383, is that what you know?
Did you write this? So this is 1383. Where did you get the 65? Sometimes I think there's,
Those two are always gonna be the same, I think.
yeah, well, not necessarily. Almost always the same. Good design is to match them. A good design, good point. Would these always be the same? Not necessarily. A good design, engineering design, they should match.
Boss can always be rated more than those.
Yes, the panel can always be rated by code more than overconditioners, but not the other way around. But a good design is always to match it, but sometimes to match it, we go to more expensive equipment. That's why we size them differently. Okay, in this case, they match, we're good to go. But not necessarily though. All right, let's go to number 3. Can I switch to 3, please? 3. Okay, number 3. Number 3, service entrance conductors. Entrance conductors. Service entrance conductors. So, you guys remember, if you're higher than 800 amp, you match the overcome. Are we higher than 800 amp? So what do? Match the overcome protection device. Always. So your rule is match over current protection device. Always. Actually, it's a good idea always to match the overcome protection device. But you have to if it's over 800 amp. Okay, so here's what I'm going to do. I'm going to take my 1600 amp, divide it on. Now I can't carry a conductor 1600 amp. There's no. So I'm going to parallel. I'm going to do 4 runs. My 4 runs will give me 400 amp. Right? So I'm paralleling. I'm paralleling. Okay? So then you take the 400 amp, take it to notoriously famous 310.15 BN16. Under which column and why? 75 degree. Oops. You take it under 75 degree column, right? And 75 degree column. I think, oops, doesn't even look like a degree here. 75-degree column, right? Anybody knows why 75? Higher than 100 amp, default 75. I came with three. Now, how many runs? We're sizing the phase. So three sets of 600 kcmthhw, okay, and right at the top of it, you're going to see four sets of three conductors. That's your answer should be. Four sets of three conductors. Four sets of three conductors. Each one of them is 600 kcm THW. Why W? If you're coming to the service, most likely almost the service coming from outside. So wet location, underground wet location. If you put 600 by itself, this is what a poor man's work is. Designers, engineers, when you guys write a conductor, if you say 4 it's meaningless. Meaningless, literally in the design. When you say, or 600, you're going to say 600 kcm, the insulation type is THW. How many of them do you need? 3 because of the 3-phase. And if you are paralleling, how many sets? Now, Darren, you're a journeyman. If I give you this info, would you be able to put PVC and pull these runs with the type of the insulation and the size? He's saying no. Don't you guys went to the same apprenticeship class? And
Yeah.
he's 110. So without saying how many conductors, I mean, it's going to be very, very explicit when you write your information. How many conductors, what insulation, how many runs. Done. Now remember, guys, you're no longer doing, Andrew, this work just for the sake of the math. You're sizing actual physical equipment, right? Kerry, my friend, we're sizing equipment. You do it all the time. Let's do the neutral. A neutral. Number four is service entrance conductor. But this time I want to say neutral. The neutral. The grounded conductor, or as we call it, the grounded boy. Okay, so let's go do the math on that boy. So remember the I neutral. Okay, now I want you guys to give me the kVA for the neutral that we calculated. Thank you. 299.8 K divided by 1.73 times 208. The most confusing thing is, why would you divide by 208 when we're sizing a neutral, Chad? What's going to happen to the neutral load, guys? All the panels are 3-phase. What do you do with the neutral load? You divide it between the phases. That's why you treat when you do the math, you treat it like we did the phases, right? With the same math. Okay, who's going to be my favorite student for the day or professional for the day and give me the answer? I need 2 gentlemen agree on one answer. 833 amps. 0.1 I'll drop. Anything less than 0.5 drop. Second, Darren? Okay. Second. All right, so here's my neutral. Now you go with this to town. Well, that doesn't mean anything to me. I need to go size a conductor to carry the neutral, right? I need to size a conductor. So let me know so we can switch to the next page to size our conductor. All right, so we're still doing number 4, neutral. Okay. So remember, how much? Give me the amps again. One more time, please.
833.
833 amps. 833 amps. Okay. Please write this one. NEC 20.61B. If you guys go to NEC 20.61B, it tells you can derate any amps higher than 200. So here's what we're going to do. I need to derate the neutral. So I'm going to go here and say derate. Derate. Here's how we derate it. The code says anything 200 amp. Here's how, if you guys go to 220.61b, it tells you if your neutral load is higher than 200 amps, right? Cut it by 70%. Is my neutral load, guys, higher than 200 amp? Yep. Can I cut it by 70%? Yep. Why? Anybody knows why? Because by the time you go to the service, guys, because you're balancing the loads on the phases, the neutral, they will offset each other. That's taking into consideration. By the time you pull everything to the service, they will offset each other and basically add each other to zero, and the neutral load will be going even lower. Okay, so the first 200, leave them alone. Anything higher than 200, which is 833 minus 200, okay, cut them by 0.7. Cut them by 0.7, and then add one more time. Anything higher than 100, 200, leave them alone. Anything, 200, leave them alone. Anything higher than 200, cut them by 0.7. Means multiply them by 0.7. Can somebody does this math and give me what the answer is?
643.1.
How much? 643 amps. Any second? Thank you. Okay. Are we done? Wishful thinking for the neutral. Now, I need to size the conductor. Now, Jeff, my friend, do you remember how we paralleled the phases? I have to parallel the neutral. How many times did we parallel the phases? Four runs. I have to parallel the neutral for, I have no choice. So I'm going to take this number, 643, and divide it by 1. Okay, do I have an option to parallel 5 here? No, because I parallel the phase 4, I have to parallel the neutral 4. So 4, what do you guys come up with? Please.
160.8.
How much?
160.8.
161 amp. Anybody's 161 amp? Everybody okay with that one? 161 amp. Okay? And I'm going to say right here, parallel. Parallel. Okay. Then, the next step, guys, is of course, 161 amps is meaningless. It doesn't mean anything. I need to convert it to a lingo that I can buy wire. So you take the 161 amps, which table? Table 310.15, B and 16. Which column? 75-degree column. Okay, Celsius. Who's my favorite for the day? How much?
4 sets of 3 wires. 2 watt.
Now, first of all, how many of them do I need? I need, first here you have to say 4 sets of 1 conductor. Okay, now that's the lingo that you use. What was it? 4 watt? 2 watt. 2 watt. 2 watt. AWG. What's the insulation? THHW. Okay? That's what this is. This calculations give you. Now, if you came up with a number here, carry less than 1 watt, and you are paralleling, can you use this number? No. If we came up with this calculation to number 1, can I parallel number 1? No. The smallest conductor you can parallel for power is number 1 watt. So that's why when you do this math and you end up with a conductor less than number 1, drop it. Use number 1 watt. Less than number 1 watt. If you're paralleling. If you're not paralleling, who cares? Only if we're paralleling. Okay. There's one more check I will do in the neutral, but for the time being, let's leave it here. I want to go back, guys, into my next step. Any question about that? So 4 sets. Can I put the 4 sets in 1 conduit? The neutral, or should I put the neutral with every set? We put 90% of the time, you put 1 neutral, 3 phase, and 1 conduit. 1 neutral, 3 phase, 1 conduit. You'll see how I'm going to draw them in a second here. So your system, I like to draw that one. Now, because your system is going to look something very similar to this, your conduits when you pull them. And I did not size the conduit, but you guys can size the conduit for me because we know how to size conduit. So in each one of these guys, here's how it's gonna, your system is gonna look like. You're gonna have one conductor, phase A, phase A, phase A, and phase A, and then you're gonna go grab. Let's use phase B. I'm using a different color here. Phase B. Oops. Phase. Come on. Phase B and phase B, and the last one is phase C. Phase C. Phase C, and phase C, and phase C. And what do you think is left? What's best? Green. What's the green? And neutral. Neutral, 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 and a neutral. And I drew this intentionally, guys, just to get you into the gravity of what you have just designed. The gravity of what you have just designed. And then right next to it, this will be four sets of 3 conductors, 600 kcm THHW, and 1 conductor, was it watt? 2 watt AWG THHW. This is what you have just designed. Okay, and I like to put how do you do black, red, blue. So that will be this will be phase A color-wise, right? Black, red, blue, right? Help me here, guys. But am I the only one who's sleeping here? Black. This is phase A. This will be the red. Will be phase B, and the blue will be phase C. And what do you guys think the green would be? In this case, it will be white. It will be N. The neutral, okay, will be white conductor, the neutral. But I don't have white on white, so I put green. But it will be a white conductor. Okay, so that's how it. And from the end, from both ends, they will be tied together. From both ends will be tied together. So I'm going to show phase only phase. I'm going to show phase B. What they do with phase B, guys, at the end here, phase B comes here, and phase B comes here. And phase B comes here, and phase B comes here. They tie them together, and the same thing, only one phase to give you the gravity. Here's phase, they come here, and they here, and they here. They all tie together, right? Not this way. They all tie to one location. And then they move. Can you guys see that? At both ends, can you guys see how they're tied together? I'm showing only one. They have to tie to the same set of lugs on both ends. That's what paralleling means. Any question, guys? That's what makes a designer from a, and at the bottom, and I can't emphasize, I like to emphasize this because once, so when you show phase A, it's going to phase A, phase A, phase A. How many of them? 4. They will be tied to at the end here. At the end here, they will be here. They will be lining to the overcompression device. From here, they will go to the transformer. Remember, there's a transformer here. So that's how they. Here's the 4 runs of phase A. I'm just showing phase A. From one side, they go to 4 lugs in the transformer, tied to the 4 lugs, tied to the same phase, and 4 lugs into the circuit breaker. And imagine this is repeated 3 more times for each phase and for each neutral. Can I get you guys to understand the gravity of parallel conductors? Everybody understand the gravity, Adam, my friend? Okay. Well, the transformer is going to be outside the building, so these lugs will be outside the building. This will be inside the switch gear, right? Because this is where the switch gear is, the main panel. So right in here, so right this in here, this will be my service panel. This is happening inside your service panel. Okay, I just want to make sure I draw the attention to the gravity of what you have just sized. You're big boys now. And Gales, do we have Gales?
No, it's not here.
You're just troublemakers. Okay. All right. I'm gonna do one thing and give you a break in a second. One more thing, because number 5, main bonding jumper. Number 5. So we did the neutral. We're gonna go number 5. You guys remember number 5 to go to the graphic. It's main bonding jumper. It's called main. Oops, not this main. Main bonding jumper. MBJ, like you said, main bonding jumper. Main bonding jumper, here's your reference in any sequence reference. You're going to go to 250.28D, and from there it takes you to table 250.66, not 55. 55 is a highway chain. That's 66. I'm going to say 55, thinking of highway 55 here. Okay, if you guys go to 250.28, it will tell you the main bonding jumper must be sized as follows. First, you're going to go to the table 250.66, which we have been there and you guys highlighted for me. And you size it based on the conductors coming to the service. If you're higher than 1100 kcm, then you have to take 12.5% of the sum of all these conductors. Okay, so let me tell you what we do here. Very, very important to do that. So here's the step number 1. How many are we paralleling? Ask yourself, are we paralleling? Yeah, how many sets? 4. So here's a 4. Number 2, what's the size of the conductors that we're paralleling for the phase? What's the size of the conductors that we're paralleling for the phase? 600, thank you. Here's a 600 kcm. Do the math. So that would be 4 times 6 is 24, and how many zeros? 0 kcm. Okay? This is the math that you have to do to size this. Okay? Now, that's step number 1. Step number 2, you're going to ask yourself, is 2400 kcm, is it more than 1100 kcm? Is that true? Right? Yes. So your answer here will be yes. If your answer is yes, then you do step number 3. If your answer is no, then you use the table, right? You use the table. Am I higher than 1100 kcm? Yep. Then you're going to do step number 1. Yes. Then you take 12.5%. I'm going to write 12.5% multiplied by 12.5% multiplied by 2400 kcm. So how do you make 12.5%? That would be 0.125, right? Can anybody, my smartest, brightest bulb on the tree, do that? 300 even? 300 kcm. Okay. Now, is 300 as an actual size, conductor size? How do you know that 300 kcm is an actual conductor size? How do I know? We know it is, but how would you know? What if you came up with, instead of 300, you came up with 295? How would I know? Here's how we're going to know. Well, then you're going to take this number that you came up with, which is 300 kcm. You're going to take it to chapter number 9, table number 8. You guys remember we used that one? You're going to go to chapter 9, table 8, and see if this is an actual size. If you guys go there, it will tell you, yeah, this is an actual size. Sleep tight, no problem. So, and then what if, here's my question for you. What if I have 290? What would you do? And you go to the table and there is no 290. And your option is 250 or 300. Which one are you going to use? 300, right? So one conductor number 300 kcm. And this could be, this conductor, this conductor, in my case, it's going to be, I'm going to use fully insulated. This will be inside the switch gear, so it's going to be THHN. But it also could be bare. Now, why THHN? It's inside the switch gear. Remember that bonding jumper? main bonding jumper inside the switchgear. It could be also a piece of cover. Most likely, it will be a cover piece inside the switchgear, not just not a wire. But that cover bar have to be equivalent to this amount of KCL. Okay, so that's your main bonding jumper. Everybody knows where we are, where the main bonding jumper is. You take the neutral, bond it to the ground. Take the neutral, bond it to the ground. I want to finish one more, and I promise you, because I'm done. After that, I'm going to size the receptacle panel. Let me finish the grounding conductor, and then we're done with that one. Then I'll give you a quick break. Okay, can I go to 6? Grounding conductor. Number 6, guys. Number 6 is equipment, not equipment. Help me here. Grounding electrode conductor, which is GEC, grounding electrode conductor. Grounding electrode conductor, guys, you need to go to the following. Your references in NEC code book will be 250.66, table 250.66 to the section, and note number 1. All these will tell you basically, if you are paralleling, then if you're doing note number 1, it tells you if you're paralleling, do what I'm going to do right now, right? 250.66 will tell you to go to table 250.66, right? And underneath it says if you're paralleling, do what Chad is going to do. And actually, they have Chad underneath the table. It's supposed to be a joke, you guys. Okay, here's what it tells you to do. You're going to take the following. You're going to take how many runs did we parallel? 4. Thank you. Take the number of runs. This is not number 1. Will tell you that. Multiplied by how many? What's the size? 600 kcnm. We just did this math. 2400 kcm, right? And then you take the 2400 kcm and you take it all the way to table 250.66, and that will get you a healthy, the largest that you can get there is what? How many of them? 1 conductor, 3 aught. 1 conductor, 3 aught. Now, is it wrong to pull 500 kcm like some engineers will do for lightning and other things? No, that's your minimum. So I get a question all the time, guys, from students who graduate and they go and they find them pulling 4 instead of 3 aught or 4 aught. And Chad, the code says 3 aught. Remember, 3 aught is the bare minimum. For safety reasons, sometimes the engineers double this. They use 400 kcm and 500 kcm. Okay? So that's your bare minimum. That's it. No 12.5%, nothing. You stop right there. Thank you. What installation, Chad? See? Yeah, thank you. And this is meaningless, Chad. This is going to be, first I want to use AWG because it's otherwise, this could be squared millimeters. Well, they don't use this one though. And it could be bare, covered, or THH. In this case, probably outside, I will use THHW. These are your options. This is the one that's going outside. So it could be covered, bare. Typically covered, guys, they use a cover insulation on it. Everybody knows what the cover versus insulated. Cover, it just gives you cover to protect the material, but it's not rated to protect you from the voltage. So the conductor, if it's covered, it looks like insulation, but it's not rated to protect you from being electrocuted if you grab on it. It's just to protect the conductor. Bare, of course, is bare. And insulated, it's fully insulated to carry current. Most likely it will be either bare. Your option for this will be either bare or covered. Green conductor. Okay, 5 minutes break, and I'm going to size a few things, and I know it's Friday, guys. I know I'm almost there. Bear with me. This is a good one, though. It's worth it.
Promise?
Promise. I think we need probably 1 more hour and then we'll done. Maybe half an hour.
So this says so the first note on there says the equivalent size.
Shall we have your presence with us? Let's do it. Receptacle panel. Now I want to quick remind you guys what we have done. Just quick, all the way, quick. Okay, here's what we've done. We sized, Andrew, my friend, we sized the main panel. Everything related to the main panel. So I'm going to remind you. Next, I'm going to size everything related to the receptacle panel, everything related to the lighting panel, and everything related to the mechanical panel. It's going to go fast because now it's straightforward. Just math. Straightforward math. No calculation. Cool? Everybody knows what the step is. All these sub panels have to be sized. So bam. Fast forward to my friends here before I lose you. Okay. So I'm going to go. Excuse me. I want to say a receptacle panel. Receptacle panel. Now for the receptacle panel, the first thing I need to find is the panel size. Panel size. I need to size my panel. So you take the current I, divide it. I need one of my friends to give me the kVA for the receptacles, the phase. 95.9. Does that ring a bell for you? Okay, cool. Wow. There's an agreement here. Okay, now I will remind you, there in the system is 28120. All the panels are 28120. Next project it will be different. There's certain panels will be 28120, others are 480. Always ask, what's the voltage system for the panel? This is everything is 28120. 1.73 times 208. I need one very competent young fella, or not so young fella, to give me the answer. What's the answer for that? What's the amp? Amp. Where's the A students? Did they go home today?
Brian's not here.
Okay, come on. 95.9 divided by 1.73 divided 26.
266.5.
267. 267 is okay? 267. Cool, thank you. 267. Then that's step one. Step two in this process, you take the 267 amps. We're going to take it to Mr. DeWalt. DeWalt under 312. Now this is 312. You can go 313. If the panels are small, they are listed in 312. If they're bigger than 600 amp or 400 amp, they flip them into switchboards. This will be a panel board, not a switchboard design. And some of you, anybody knows the difference between switch gear design and switchboard and panel board? If you don't, welcome to the club. That's what we'll be learning as we move forward. Long story short, panels, guys, will be mounted against the wall. Switch gears will be for the most part, right in the middle of the room, like a refrigerator, versus a panel on the wall. Okay, so for this one, what's the size? 260. Do I have 300? Do I have to go 300? Can you guys, 300 is the next. What's the next lower? 225. So my option is 225 or 300. I'm going to go always up. 300. 300 amp. 300 amp. So my panel size will be 300 amp. 3-phase, 2-way panel. Okay, number two. So I size my panel 300. Overcurrent protection device. The feeder overcurrent protection device that's going to feed the panel. Now remember, that panel is going to be fit. This panel is going to be main lugs only, right? But there will be a feeder ahead of it in the main panel that feeds it. That's what we typically do. We have a feeder in the main panel, and there's overcurrent protection device to protect it and protect the panel, and the panel itself will be main lugs only. Okay, so again, 240.6. So you're going to take the 267 amp, take it to 240.6. That will get you now 240.6. That will give you what? What's the next standard? Do I have A 300? I don't have any 375, right? 300. 300 now. Cool. This is actually the best design when you match the overcome protection device to the panel size. You don't have to match. The overcome protection device can be slightly or substantially lower than the panel. But what's the problem with that? It's not a good design. You almost want them to be the same as much as you can do. Okay, shall I go to the third? Okay, so you guys are getting the swing of that thing. Okay, so let's go. What's 3? My third is going to be feeder. 3. Now, I'm using the term feeder. What did we use with the service panel? We use service entrance conductors. These are feeder conductors. Completely different article. So feeder conductors. And then we'll put phase for the phase. These are just the phase here. Okay. Now here's what I want you guys to do. 240.4b. 240.4b would tell you. First of all, give me the amps. What can you guys give me the amps of the load? The load amps. Was it 267 amps? If you go to 240.40b, it allows you to size the conductor based on the load. You can grab the 267 and size the conductor based on the load. Cool? It allows you. Now remember, we're engineers. It's not a good idea to do that, even though the code allows you to do it. Am I clear about this? So if you see it done in the field, if you're 800 or less, you can size based on the load as long as the next standard overcome protection device is higher. Once the next standard is the overcome protection device. Like for this, is there any overcome protection device between 267 and 300? No. So if I put 300 to protect 267 cable, that's okay, acceptable. Up to 800. After 800, what do you start doing? Match the overcome protection device. But I want you guys to get into the habit of matching the overcome protection device. Having said that, I'm going to say my overcurrent protection device equals 300 amp, and I'm going to write right here, match overcurrent protection device. Okay, so even though I told you can size based on 267, we're going to match overcurrent protection device. Good design. So people don't scream at me when they go through that one. Good design. If it's higher than 800 amp, it's not just good design, it's code requirement. Here's its good design. Okay, so I told you that, so you guys are so I have 300 amp. Take this one to table 310.15 B 16 under 75-degree column. Well, what's the size?
350 KC.
Okay, so here's how I'm going to do it because we're into the parallel. So it's going to be one set of 3 conductors. How much?
350 KC.
350 kcm. Now remember, these are feeder inside the building. 99% of the time they're going to be in what? In a dry location, in an EMP conduit. So what type of insulation do I use? EHHN. This is what a good designer would do. Write exactly one set, not 2, 3 conductors for the 3-phase, 350 THHN. Done. Okay.
Not derating the neutral.
We're coming to the neutral. This is just the phase. This is the phase. Can you see that we're sizing the phase? I want to go size the neutral. Can I flip to the neutral? Flip to the neutral chair. Number 4 is feeder neutral conductor. Feeder neutral conductor. Okay, so let me just size I neutral. Can you guys, here's my I neutral. What was the kVA for the neutral in this panel? It was the same like the phase, right? How much?
56.9.
No, the kVA. Actual kVA on the neutral.
Yeah, 56.9.
Was it 56? 6.9, okay, K. Divide this by 1.73 times 208, and we got, what did we get? We did that one,
You get one, oh, I got 158.8.
are we, which one are we looking at here?
Because we didn't carry the 39 from the.
Yeah, because we didn't carry the 39. Okay, gotcha. Okay, no problem. Give me that. Then it's a new calculation. Yeah. What was that again? How much?
158.
158. Any second? Second. Okay. Now, the second thing, is this 158 more than 200 amp? The answer is no. Then what? No derating, right? Otherwise, you're going to apply the derating that we did. Is the 158 more than 200? No, so you can't derate. Remember how we derated more than 200? There's no derating here. So sleep tight. And this is, of course, the derating, if you guys remember, come from, where am I here, Chad? Neutral, 220.61. The whole derating business. Okay, so there's no derating. So let's go size. Let's go size neutral. So 158 amps. Go to table 310.15 B and 16, 75-degree column. One conductor, one set of one conductor 2-aught AWG. What insulation? THHN. Done deal. Done deal. So what was the phase? The phase was 350 and the neutral was 2-aught. Now a lot of engineers, guys, they either, for panels up to 300 amp, they match the neutral to the overconduction device. They match the neutral, they make them the same, up to 300 amp. Higher than 300 amp, it would be a fool to make them the same. So between 200 and 300, up to 300, it makes a lot of sense to size the neutral the same as the the phases. Higher than 300, fool. Okay, but we're gonna apply the rules. My rule right now is right here. Okay. Any question, guys, about my 2-aught conductor for the 300 amp panel? So if you go work for somebody, Darren, and they tell you we're gonna pull a full neutral 350, are you violating the code? No. For safety, future, whatever reason, up to 300 is a good idea. Higher than that, no, not really. Okay, number 4. Number 5, what was number 5? Number 5, equipment ground conductor, right? Number 5 is equipment grounding conductor. This is your equipment grounding conductor, right? It's just not, you put the brackets here, you confuse. Equipment grounding conductor. For the equipment grounding conductor, guys, your reference is the following. Your reference is, it's going to be 250.122 section and table 250.122. Section and table. So a piece of cake, Chad. Let's go ahead. And so what do? We take the overcurrent protection device of the system, which is 300 amp. From there, we take the 300 amp, take it to table 250.122. Who's my favorite? We're using copper. Who's my favorite buddy that was going to tell me one conductor, and what's the number 4 AWG? That will be THHN, typically THHN conductor for the equipment ground conductor, if any. Or it could be bare. Typically, if it's in a conduit, it's going to be THHN or covered. Okay. One conductor. If we parallel, then we have to put one in every conduit. Okay. We calculated the phase, we calculated everything else. I'm going to flip into the lining panel. right away. We're going fast. Lighting panel. So let's do the lighting panel. Lighting panel. For lighting panel, let's do the same thing. Who's my favorite here? I want the size, panel size. Panel size. I equal. What was the KVA for the phase for the lighting panel? Can one of my friends give me the KVA for the lighting panel? 242.5 K. Divide this by what? 1.73 times 208. Where's my friends? Where are my friends? 600.
74.
74. I'm getting old, man. I can't hear these days. Okay, amps.
Me too, too many saws on the job site.
So we saw it. Okay, now 674 amps. You're going to take this boy into where? Where we have been going all the time. Amps. You're going to take it to DeWalt 3-12. What's your next standard? Is it 3-12 or 3-13? 313 because you ran out of panels at this. 313. What do you come up with? 800 amp. Now 800 is. By the way, is there a 600 amp panel? Yeah. Now here's where a judgment. See where you become an engineer, you make a judgment. My option, here's my load. I have two options. I can go by code. I have to go up to 800, or if I'm an engineer and I'm willing to stick my neck and sign up on it, I can go down to what? 600 amp. So Kerry, if you go work on a project and the engineer said, I want to go down to 600 because cheaper equipment, is that wrong? No. These are all estimates, guys. Okay, as long as you can justify it, justifying it by experience, by whatever, knowledge of the material, I can easily on this project, personally, I can jump it to 600 amp if it's my project, instead of going to 800. But we're going to use the rules in the book here, though. We're going to go to 800 amp. Thank you. Next. The next one is going to be what? Overcurrent protection device. So same calculation. You're going to take the 674 amps, take it to where? 240.6, and that will give you, what's the next standard? Do we have 700? Can you guys verify that one?
Yes, we do.
Thank you. So now we'll get 700 amp. By the way, this is a good idea. Can you guys see that the panel size is slightly bigger than the overconfiguration device? That's a good idea. Otherwise, if you go to 800 amp, the cable will be 800 amp too. So you're oversizing a cable and so that's why, see how they're different now? They are different. But the panel must always be equal or more than the overconfiguration device. Yes, we could have, yes, absolutely. I could have brought the panel down to what? 600, and I brought my overconfiguration device down to 600. Why would you do something like this? Cheaper equipment. Again, if you're willing, you know from your experience, would I do it if it's my project right now? Yes. For this amount, 67 amps, right? Or 74 amps, I drop it down to 600, size for 600. But be very careful though when you do that one. It has to be engineering project and people feel comfortable with it. So if something to go wrong, for example, and you go to court, and I will review your work for the court, and I see that you went down and you burned some equipment, you lose a case. That's kind of why people go up all the time, the safer. But a lot of engineers go down for value engineering, so-called value engineering. Okay, but we're going to go what? We are doing the extreme here. You can't believe how many people went in the field and say, Chad, my boss went down. You can't go down. Engineers can do anything. I can design as a registered engineer right now. I can design anything I want. But guess what? I can lose my house if it burns. Does that make sense? Am I clear about this one? That's why we use the Bible. You use the Bible or what? You stick with it. Okay. So where are we here? Number 3. We got that one. Number 3. What was number 3, guys? Feeder conductors. But these are the phase. Okay. excuse me, for feeder conductor, guys, I can have two options. I have 674, right? So here's what I'm going to show. I have my I equals 674 amps. Because 674 amps. Because of 240.b, I have two options. Am I less than 600 amp? 800 amp? Yes, I have two options. Either I size the cable based on 674, okay, or I match the overcurrent protection device. What do you think engineers would do? Match the overcurrent protection device. A lot of contractors actually size based on 674. It might not make a difference in this case, but in a lot of cases it would. So, okay, here's your amps. Then I'm going to say also come over here, overcurrent protection device equals 700. And I'm going to write next to it match overcurrent protection device. Right note to it, design. Good design. Okay, can I get that one, guys, through to you? Good design. Okay, having said that, then it becomes a piece of cake, right? So you're going to take the, okay, we're here for overcurrent protection device feeders. We're going to take the 700 amp. Now, remember, 700 is a lot of amps to carry in one conductor. By the way, every time, Joe, you go higher than 400 amp, always parallel. Did you hear me? You cross the border of 400, what do? Parallel. It would be fool not to. So what's the cutoff? 400. Okay, am I higher than 400? Yep, Chad. So divide this by what? Let's do 2 sets, because that's easy, 2 sets. I'm going to do 2 sets that will give me 350 amp. I'm going to call this is parallel. Okay, then you're going to take the 350 amps, take them to notoriously famous table 310.15 B16 under 75-degree column. What do you get? How many sets first? Let's write the sets. 2 sets of 3 conductors because it's 3 phase. What's the size? 400? 500? 500 kc. And what insulation? THHN. Why? We're inside the building between panel to panel. Done. So we are pulling 2 sets. Move to number 4. Okay. Number 4. All right. So number 4. What's number 4? Number 4, feeder neutral. Feeder neutral. Remind you of 220.61. Remind you of that one. Okay, what's my neutral current? I neutral. Can you guys give me, I think it's the same, the lighting is the same. What's the load for the lighting? KVA. How much? 242.5 divided by 1.73 times 208. It's the same calculation. So what did we come up to with 674 amps? Okay, so that's the same calculation, right? Because the load of the neutral was the same load. So no gimmicks, nothing. Okay, then remember we derate for neutral though. Are we higher than 200 amp? Yep, derate. So then we're going to take the 674 amps, take them to the first 200 amp. What do you do with them? Don't you ever mess with them. Higher than this, 674 minus 200. You multiply this by what? 0.7. And who's my favorite student for the day? Who's going to give me the answer?
531.8.
532 amps. Second, thank you. Okay, now that I derated the neutral, I have 532 amps. Now I have no option but to parallel. And how many sets? 2, because I parallel the phase. So divide by 2, give me what? 266 amps. Then you're gonna take the 266 amps to where? 310.15 B16 75-degree column. And okay, here's what I'm gonna write. I'm gonna write 2 sets of how many conductors? Okay, number 1. Okay, 1 conductor, and it has to be 300 kcm. What insulation? THHN. That's, now you're my friend. 2 sets of 1 conductor. Okay? Almost there. Hang in there. There's light at the end of the tunnel. So I go fast on these because we're repeating ourselves. I can't emphasize. I want you to come out of here, guys, know how to do all these. Okay, let me know when I can flip to the last thing on this panel. Andrew, can move on? Everybody? Okay. Number 5. What was number 5 again? Equipment grounding conductor. Number 5 is equipment grounding conductor. Table 250.1, 2, and 2. We size this one based on what? On overturned protection device. Always. Okay, so let's go do that. Huh? Let's take the overturned protection device 700 amp. Take this boy to table 250.122. We're engineers, so we're vested in the cover companies. We don't pay for the cables. So what size and how many conductors? 1 conductor, 1 aught, AWG, most likely THHN, covered or insulated, covered. Could have covered ones, green covered conductors. Thank you. We need to, we're paralleling. I forgot that we're paralleling. So that will be 2 sets. You guys are on. Thank you. Yeah. 2 sets up. 1 aught. So you're going to put 1 conductor with every conduit. So with this, I like to do my graphics here very quick, very fast, show you what these are going to look like. Let's go back into our phase A. Here's my phase A. Let's go back into phase B and phase C and neutral. And also this time we need a ground. Okay? Same thing here. Here's C, here's B, here's a neutral, and here's a ground. Okay? So here's what your 2 conduits are going to look like. So when you write them down here, guys, you're going to say 2 sets of how many conductors? 3 conductors. What was the size? The phase size. Quick. 500 kcm THHN and 1 conductor. It was neutral 300. 300 kcm THH. Oops. THHN. THH and 1 conductor, 1 aught, AWG, also THH and Orbea. This is how your system is going to be. Can you guys see that? Do you see the ground? There is a ground in every one of these. I can't emphasize. This will be your phase A. This will be your phase B. This will be your phase C. This will be coming from here. This will be your neutral. And the other one will be your ground. Now, do I need a ground if I'm using EMT? No. So that number 1 aught might not be used because we're using the EMT conduit. You only use it if you're using non-metallic conduit. Am I clear about this? And you have to put the equivalent ground conductor with every conduit. That's the rule, every conduit. Even though we really didn't parallel here, but we have to, if you're paralleling, you have to stick it with every conduit, the same size. Yeah, if it's non-metallic conduits, you need an equivalent ground conductor. If it's metallic conduit, you can use the conduit itself, EMT, rigid, intermediate, to use it. If you're using flexible metallic conduit, also use it. The only time you do not need it if you're using EMT, rigid, or intermediate. Am I missing any of the others? Every other wiring methods, busways if you're using busways too, and cable trays if you're using cable trays.
Real world though, you're always gonna pull it down.
Thank you. A lot of good engineering design, a lot of engineers don't like to depend on the conduit to pull, especially for feeders. Branch circuit is not a big deal, but for feeders, they don't like to depend it, so they push a ground in it. We're almost there. The last panel. The last panel is going to be my so equipment ground conductor. We'll get that one. We got lighting. Mechanical panel. This is good. I want to do it. I'll give you a homework another one. Let's just do that one. Mechanical panel. Let's do that one. Because the reason why I do that one, because there's something I'm going to emphasize about this. A three-phase and a neutral. The three-phase and neutral. Okay? Let me emphasize that one. That's really the reason why I want to do it. Not because I like to listen to myself. I do like listening to myself, but not that much. Panel size. Panel size. Okay, who's my favorite is going to give me the KVA for that panel? What was the KVA for the main panel?
159.
50.
159.
1, 5, and 9 KCN, not KCN, Chad. 159 kVA. Divide by 1.73 times 480. Not 480. Times 208. 208. Who's my favorite? 442 amps. That's about it. The 442 amps. Okay. All right. So then you take the 442 amps. Take it to DeWalt 3-12. What's your next standard panel?
600.
Thank you. 600 amps. What's your next standard down? 400. Now here's a judgment. I either go 600 or 400. See the jump in the difference? That's where another application where an engineer walk in and say, "Are you kidding me? We'll just put a 400 and call it a day. We're not far away from 400." Huh? Yeah, 10, 15, a quarter, yeah, will be more than a quarter, definitely you go up. Yeah, judgment, absolutely. Less than a quarter or less, if you want to put a value on it. Yeah. Sometimes we stretch it to a third or less even. Okay, so then that's it. Then let's do the overcurrent protection device. Number 2, overcurrent protection device, same calculation. 442 amps. You're going to go to which table this time? 240.2. Who's my favorite? Is going to give me, do I have 450? Oh, I didn't write 2, did I? Oops. Not 6. Do I have 450 or I have to go 500? Can you guys check? I don't think we have 450, but there is? Oh, they didn't tell me that they're making them. That must be new in the last 100 years. Probably. 450, right? 450 amps. So 450. Here's your overcompression of 4. But you can see the panel. Now this is where it becomes weirdo. You have a panel of 600 and overcompression device ahead of it is 450. It's okay. Remember, we are sizing. Now the cables will match. Which one of them the cables are going to match? The 450. Oh my God, you go to 600. Imagine the cables. Now you oversize it. Okay, so if I may go to number 3 here. Number 3, that will be panel or feeder. All of them are panels. This will be a feeder conductors. And this is phase. Feeder conductor phase. Okay. Now I want you guys to give me the size first. The load. What was the load? What was the load for something?
442 amps, and the overcurrent protection device is 450. Okay, now remember, you can size up to 800 amp, you can match the load. You can match the load. Good design, what are we gonna do? Match the overcurrent protection device. So, good design, so match overcurrent protection device, good design. Disclaimer. And okay, so 450. So let's go to 450. Take this boy to table 310.15 P and 16, 75-degree column. Who's my favorite? Shall we pull one conductor or parallel? That's where it becomes you're higher than 400. Let's pull. What did I do here? Did I parallel? I pulled the full conductor here. I pulled the full conductors. That's where really you might have 700 are big, so you might have to parallel. But let's just pull a full conductor for this one. So what do I have here? I have 3 conductors, 700 kcm, THHN, 1 set of. This is your answer. If you show this one to an electrician, say, are you kidding me? Do you want to pull and terminate that boy? Okay, so that's why we know how to parallel if we want to, right? Divide by 2 and parallel. All right, so feeder neutral. Let's do the neutral. Number 4. Feeder neutral. Remember the 220. What was it? 220.61. So I'm going to take my amps. What was the I for the neutral? Give me the kVA, will you? 0 divided by 1.73 times 208 equal. Anybody knows what 0 divided by anything? Equal big fat 0. Okay. Neutral conductor. So this is where, how you decide the neutral? In the mechanical panel. That's why I wanted to do that one. The question would be, the reason why we have mechanical panels, guys, is because we do not need a neutral. All of them are 3-phase. So that's why you might end up with, in a panel, a mechanical panel that has no neutral. They just don't have a neutral. The panel does not need a neutral, just a 3-phase panel. The kitchen equipment, we shifted them. Yeah, we shifted them. Yeah, remember, if you look at all the panels, the mechanical panels, if all your equipment does not have a neutral, then you don't have to size neutral. You don't have to have a neutral, okay? You don't have to have a neutral. Now, so that's where you're gonna use a kind of a judgment where we don't have to have a neutral.
What would you pull one for future?
Now,
More than likely.
Now again, that's judgment. That's judgment. Judgment based on what we have. If this is exactly what we have on our load, I wouldn't put neutral. Now, if I don't know and I want for a future, like you said, then I would probably, so I would say one solution is no and conductor. That's solution 1. I don't need a neutral. Solution number 2, I need to size a neutral, and the only thing, so you don't pull neutral, but if you want to have a neutral there just in case, well, where's your start point? A start point would be, how about if I assume all this junk is neutral and size based on this? That's a good assumption. Assumption. It is not neutral. That's the only load that I have. I have nothing to go with. So again, do you see how I did that one? I'm going to assume assumption that this load here 442 amp equal I neutral. I'm going to just use this because the only value that I have to size by is this, right? Then I'm going to go apply the rules for it. Remember, we can apply 442, apply the rule for it. The first 200, what do you do with it? Leave it alone, higher than 200. So 442 minus 200, the derivative times 0.7, and give me the answer, will you?
370.
70 amps, okay? Here's my amps for a neutral. If you wanna, which is a good idea, is to have a neutral on the panel just in case for neutral. But if I know when I design, you guys will design a system. You look at all your mechanical equipment, not a single one of them has a neutral on it. There is no future neutral. If I have a future mechanical panel that need a neutral, where do you think I shift it? Receptacle panel, right? Not a good idea, but I can shift it to receptacle panel. Then I can go with no neutral. But we decided because we don't know, we're gonna put full neutral. So let's go size that boy. Then I'm gonna get number 4. We're still doing number 4 here. So what was it? 350? 350 amp. Take this one to 310.15 B16 and there's 75-degree column. That will get you. How many sets do we have? We didn't pedal, did we? We didn't pedal. So it's going to be one set of one conductor. What's the size? 500 kcm THHN. That's would be a little bit overkilling even on that system. So that's very conservative, really, to pull that one. A lot of engineers guys come and take the size of the phase and drop 2 to 3 steps below, you know. So 700, what's the next step? 600, I think. Right. Go one more step, 500. Go one more step, so 2 steps. So from 7, you go 1 step, they'll get you 6. 1 more steps is 5. And you can even a little bit go to, what's after 5? 450? 4. Yeah. But if you don't know, it's a good assumption to use the, basically, we're almost kind of not matching the neutral. We're not matching a neutral, but going by the actual load. That's a good assumption. A good assumption. Okay, the last thing, and then I'm done for good now. Equipment grounding conductor. This is your 250.1, 2 and 2. Overcurrent protection device, what was it? What was it, 700? 450. Am I still stuck with the first one? 450, 450 amp. Then what do? You take the 450 amp, take this boy to table 250.1, 2 and 2, and that will get you how many? One conductor, first one set of one conductor, what's the size? Number 2 AWG THHN. Done. And then your conduit will look something very similar to this. I'm done. Here's your phase A, phase B, phase C, and your neutral and your ground, right? So this will be my ground, this will be my neutral, this will be my phase A, this red will be my phase B, and this will be my phase C. I'm just throwing these one so graphically you appreciate what we're doing. Any question, guys? What I'm hoping, Kerry, I know it took me 3 hours with you guys almost. What I'm hoping by going over this and the load calculation, it cements your full understanding of what a riser and one-line diagram sizing is. What a riser and a one-line diagram sizing is. Okay? So the last thing, I want one of my best friends just to give me one thing. I'm going to write them here, and you guys are, I'm off your hair here. Remember when we started with the panels? Good grief. Okay, the last thing, I'm going to just going to give me the size. What was the main panel size that we came up with? Was it 1600? The panel.
Yeah, that sounds about right.
1600. Where's my friend?
Yeah, 16.
Okay, the panel was 1600 there. Okay, what was the overcome protection device? 1600. I'm just going to put them here, 1600. Let's go to this. The mechanical panel was 450, right? The actual panel was what? This is the overcome protection device. The panel, the actual panel was 600, right? The lighting panel, what was the lighting panel? The panel was
Panel 800 amps.
800 amp, the panel. What was the overcome protection device? 700. Thank you, 700 amp. The last thing is the receptacle panel was 300, both of them. 300 amp. and 300 amp. You guys see where the amp is located, and the rest I'm not gonna write the cables. You can see the cables. The rest and the cables are there. Any question? Okay, that's all I have. I want to remind you guys that you need to print your stuff for me and continue working on your load calculation. Thank you.